박희성 교수님 시작해도 되겠습니까?
예, 좋습니다.
네. Okay, welcome to the AGEA seminar, everybody. And the first speaker of today is Professor Isong Park from Korea University, and the title is On the Rank of Quadratic Equations of Projective Varieties. Please.
Okay, so thank you very much for inviting me to this seminar and giving me this opportunity. And yeah, as it is mentioned, the title is the rank of quadratic equations of projective varieties. So, and maybe during my talk, I have to turn off the video because otherwise you can only see my hand. Okay. Okay, my talk consists of 4 sections, and firstly, I will talk generally about the rank of quadratic equations of projective varieties. So in my talk, the base field K is algebraically closed, and the characteristic is not equal to 2 because I mainly consider the rank of quadratic polynomials. So over characteristic 2, the rank is not well defined. And the pair x, L denote the projective variety x and the variant line bundle L on x. And here x in PR is the corresponding linearly normal embedding of x by L. So here R is the dimension of the global section of L minus 1. And here R denotes the homogeneous coordinate ring of PR. And I of x, L is the homogeneous ideal of x in this space. So here I have to vary the line bundle L. So here the homogeneous ideal I denote by x of I of x, L. Then a classical problem is to find the condition that the homogeneous ideal is generated by only quadratic polynomials. So this would be the simplest case if we consider the degrees of the generators. And there have been many interesting results about this problem. And among them, here I want to remind you of the following Ein and Lazarsfeld's result. So here, if x is a smooth complex variety and the dimension n, and if A is a variant line bundle on x, then the following line bundle L defines an embedding such that the ideal is generated by quadratic polynomials. So the condition is as follows. Here, Kx is canonical line bundle of x, and here the n plus 2's power of A is multiplied. So if L is positive than this line bundle, then the corresponding embedding is ideal theoretically cut out by quadrates. And here, this condition can be written as follows. So this line bundle is NF if and only if the line bundle L is this fixed line bundle times B, where B is a NF line bundle. So if we consider the ample cone of X, then the canonical bundle times n plus 2 powers of A will be always very ample. And the theorem says that if we move this ample cone by kx times n plus 2 times A, then we have again a cone. And the theorem says that any line bundle contained in this cone defines an embedding such that the ideal is generated by quadratic polynomials. So what I want to say is the property that ideal is generated by quadratics is satisfied by many line bundles on X. And next, I consider another more structural property of the homogeneous ideal. So here X comma L and X in PR as the beginning. Then we say that this pair satisfies this pair is said to be determinantly presented if there is a matrix such that the ideal is generated by the 2 by 2 minus of this matrix. So the matrix M has entries in R1, where R is the homogeneous coordinate ring. In other words, the entries are linear forms. And the ideal of X is generated by the 2 by 2 minus of this single matrix. In such a case, we say that X comma L is determinantly presented. So this will be a nice structural property of the homogeneous ideal of the projective variety. And here I will give two examples. First one is the twisted cubic curve. So C is embedded by O3 on P1. And then this element that the ideal of C is generated by the 2 by 2 minus of this matrix M. So here, if you restrict this matrix to C, then you can see that the first row and the second row are linearly dependent, and hence the ideal C satisfies all 2 by 2 minus of this matrix. And indeed, moreover, the ideal of C is generated by those 2 by 2 minus of this matrix. And hence, this is an example where the pair is determinantly presented. And more generally, any rational normal curve is determinantly presented. Here, again, there is an appropriate matrix M such that the ideal of C is generated by 2 by 2 minus of this matrix. And there have been many examples of determinantly presented varieties. And for example, any Veronese embedding is determinantly presented. And this was shown in 1989 by Fuchi. And so every rational normal scroll is determinantly presented. One may see, one may describe the matrix M for each rational normal scroll. And the Segre variety of two projective spaces is determinantly presented. Indeed, here the space PR is nothing but the space of A plus 1 by B plus 1 matrices. And the Segre variety is nothing but the rank 1 locus of such a matrix. So it is defined by the 2 by 2 minus of this A plus 1 by B plus 1 matrix. So it is determinantly presented. And if you consider the triple product, then it is known that this variety is not determinantly presented. And I So this result in a paper by Jessica Seidman and Gregory Smith. So anyway, if the Segre product of more than 3 spaces is always fail to be determinantly presented. And in this direction, the first general result was obtained by Eisenberg, Gu, and Stillman in 1988. They studied this problem for projective integral curves. If C is a projective integral curve of arithmetic genus G, then any line bundle L of degree bigger than 4 times genus G plus 2 is determinantly presented. So roughly speaking, any sufficiently large degree line bundle on an integral curve has the property determinantly presented. And then David Eisenberg wrote several textbooks, and among them, on geometry of series, Eisenberg provides an exercise problem which says that this type of property will hold for arbitrary projective varieties. And then in 2012, Jessica Seidman and Gregory Smith proved this, in some sense, exercise problem. So when X is an arbitrary projective variety, they proved that there exists a line bundle A on X such that XL always satisfies the determinant presentation if L is positive than A, namely L times A inverse is ample. So again, if we consider the ample cone over X, then their result says that there exists a line bundle A such that if we move the original cone by adding A, then any line bundle on this cone is determinantly presented. And in this talk, I mainly consider the rank of the quadratic polynomials. So yeah, I want to mention that if X is determinantly presented, then automatically we can say that the ideal can be generated by quadratic polynomials of rank and most 4. Here, let me remind you of the basic property of the rank of quadratic polynomials. If there is a non-zero quadratic polynomial Q, then there is an associated symmetry matrix R plus 1 by R plus 1 matrix. And I denote this matrix by M subscript Q. Then the rank of Q is defined to be the rank of this symmetry matrix. And in undergraduate linear algebra, we learned that the rank of Q is equal to L if and only if Q can be written as the sum of L squares of linear forms which are linearly independent. So we can read off the rank of Q from the associated matrix. And for example, yeah, G0 times G1 is of rank 2 because it can be written as the sum of 2 squares. And G0 times G1 minus G2 square is of rank 3 because here again it is written as the sum of 3 squares. And this type of equation is obtained from the determinant of 2 by 2 matrix. So this type of equations appear in the homogeneous idea of many rational varieties. Where here, so concerning the rank, I want to introduce a notion. So x comma L and the x in PR as in the introduction. Then we say that this pair satisfies the prop QR of L if the ideal can be generated by quadratic polynomials of rank and most L. And here I also want to introduce to another notion which is typically used in algebraic geometry. So we say that a property P holds for a sufficiently ample line bundle on X if there exists a line bundle A such that X comma L satisfies such a property P if L is positive than A, in the sense that L times A inverse is ample. And today I mentioned a few such properties. So namely the following properties P hold for sufficiently ample line bundle on X. So firstly, P is the property that X comma L is determinantly presented. Then by the theorem of Siedman and Smith, this property holds for sufficiently ample line bundles on X. And this implies that the following property holds also for sufficiently ample line bundles. P is now the property that the ideal is generated by quadratic polynomials of rank and most 4. And we can replace to this property by property QR4. So property QR4 holds for all sufficiently ample line bundles on X. And also we can say that the property that the ideal is generated by only quadratic polynomials is true for sufficiently ample line bundles on X. So at the beginning, I mentioned a work or result by Ein and Rajasfeld, and their result is about smooth complex varieties. And here, if we use the Siedman and Smith's theorem, then indeed we can say that the property that the ideal is generated by quadratic polynomials is true for sufficiently ample line bundles on arbitrarily irreducible varieties. Where finally, if Q is a non-zero quadratic equation of X, then indeed the rank of Q is at least 3, and obviously at most R plus 1. This is because the rank is, if the rank is 2 or 1, then the quadratic equation is a product of linear forms. But our X is irreducible and non-degenerate. So there does not exist such a degenerate quadratic polynomials. So for irreducible projective varieties, any non-zero quadratic equation has rank at least 3. And up to now, you know that property QR4 holds for sufficiently ample line bundles. So my colleagues and I asked to ourselves if we can improve this bound of rank. Namely, we consider the following question. So does the property QR of 3 hold for sufficiently ample line bundles on X? Okay, so today, indeed, I want to give a partial answer for this question. And firstly, I want to revisit the following example, twisted cubic curve. So you know already that the ideal of C is generated by the 2 by 2 minus of this matrix. So it is generated by rank 3 or rank 4 quadratic polynomials. And more precisely, the ideal is generated by these 3 quadratic polynomials, which come from M. And here Q1 is of rank 3, Q2 is of rank 4, and Q3 is of rank 3. And so we know that this satisfies property QR of 4. And our question is whether this curve satisfies property QR of 3. And to this aim, we have to find more equations, more quadratic equations of rank 3. So to find such rank 3 equations, I consider arbitrary general element of the degree 2 part of the ideal. We can write Q as A times Q1 plus B times Q2 plus C times Q3, where A, B, and C are some constants. And we want to find the constants A, B, and C such that this quadratic equation has rank 3. So we use this symmetric matrix associated to Q. So for example, the coefficient of G1 square is minus A. So here, the second diagonal is minus 2 times A. And the coefficient of G0 times G3 is B. So this entry and this entry are equal to B. So anyway, from Q, we can write down explicitly the symmetric matrix M subscript Q. Then the rank of Q is 3 if and only if the determinant of this 4 by 4 matrix vanishes. So the rank 3 condition is obtained from the determinant of this matrix. And if you calculate the determinant, then it is the square of B square minus A times C. So theoretically, the determinant of MQ is a plane conic curve. So for example, if A, B, and C are equal to 1, then the determinant of this matrix is 0. We can find more quadratic equations of rank 3 by using this determinant. And for this case, Q, namely Q1 plus Q2 plus Q3, can be rewritten as G0 plus G1 times G2 plus G3 times G1 plus G3 squared. And hence, as it is expected, Q is a quadratic equation of rank 3. Okay, so we find a new equation of C whose rank is 3. So obviously, the ideal of C is now generated by Q1 plus Q2 plus Q3 and Q3. And these three quadratic equations are all of rank 3. So we have an example such that property QR of 3 holds. Namely, the twisted cubic curve satisfies property QR3. Okay, now I want to mention our main theorem concerning the rank of quadratic equations of projective varieties. So our finding problem was that the property QR3 holds for sufficiently ample line bundles, and we get the following partial answer about this question. So this theorem was proved by following 4 people. This is Kang-Jin Han, and this is Wan-Seok Lee, and this is Hyun-Sung Moon, and this is me. And the statement is as follows. So we suppose that the characteristic of the base field is not equal to 2 and not equal to 3. Then every Veronese embedding of Pn satisfies property QR of 3. Indeed, if the characteristic is not equal to 2 and 3, then all Veronese embeddings share the property QR of 3. And here I exclude the case where characteristic of K is 3. And in such a case, we have the following interesting case. If the characteristic is 3, then the second Veronese embedding of Pn satisfies QR of 3 if and only if n is 1 or 2. So if n is 1, then this defines a plane conic curve. So obviously its equation is of rank 3. And if n is 2, then we get the Veronese surface. And again, this Veronese surface satisfies QR3, whatever the characteristic of K is. And in the theorem, it is mainly proved that the second Veronese embedding of P3 fails to satisfy QR of 3. And then by using the n equal to 3 case, we can prove that or n bigger than y equal to 4, the second Veronese embedding fails to satisfy QR of 3. And in this case, the ideal is generated by 20 quadratic equations. And if the characteristic is not 3, then you can find the 20 rank 3 quadratic equations. And in characteristic 3 case, this is not true. So one may ask, what happens if you restrict the quadratic equations in characteristic not equal to 3 case to characteristic 3 case? And if you start with the 20 quadratic equations of rank 3, if you restrict it to the characteristic 3 case, then it happens that among the 20 equations, 2 of them are same if you change the base field. So anyway, the characteristic 3 case is some strange case concerning property curve 3. Okay, here I want to explain an idea, a sketch of the proof of this theorem. The first X is the Veronese variety of Pn by degree D forms, and capital N is the dimension of the ambient space. And R is the homogeneous coordinating of Pn. And sigma is the set of exponent vectors of degree D forms. So it is a set of n plus 1 tuples consisting of non-negative integers, and the sum is equal to D. So the variables, the homogeneous coordinates on the ambient space can be parameterized by sigma. You can write the homogeneous coordinate ring of the ambient space as the polynomial ring generated by the variables parameterized by sigma. And it is well known that the homogeneous ideal of X is generated by this type of quadratic equations. So here, I, J, K, and L are elements of sigma. So they are the exponents of some monomials on Pn. And if I plus J and K plus L are same, then this quadratic equation restricted on X will be 0 because the exponents of two monomials are same. So one can easily see that this type of equations are contained in the homogeneous ideal of X. And a well-known fact is that the homogeneous ideal of X is indeed generated by this type of quadratic equations. So to prove the prop QR of 3, now we have to find a set of quadratic polynomials of length 3 whose span in this space contains all members of this generating set of the old generating set of the ideal. Namely, we need to produce many rank 3 equations of X. And to this aim, we consider the following map. So firstly, pi is the following isomorphism. So Rd is the space of D forms, and S1 is the space of linear forms on the ambient space. So by sending x to the I, this type of monomial to Zi, we get an isomorphism, and this really defines the Veronese embedding. And then, in order to produce the rank 3 equations, we use the following map. So here, R1 times Rd minus 2 to the ideal of X. So here, F, G, and H are forms on Pn of degree 1, and D minus 2. So F square H, G square H, and FGH are forms of degree D. Then by pi, you get linear forms on the ambient space. So this is a quadratic polynomial on the ambient space, and we can observe that indeed this quadratic polynomial is contained in the homogeneous ideal of X. This is because if you restrict this form to X, then you have f square h times g square h minus the square of f2h. And hence this is obviously zero because the polynomial ring is a commutative ring. Okay, so the commutativity of R implies that this type of element is contained in the ideal of X. So in this way, by using this map Q, we could produce many rank 3 equations of X. Then we could prove that these rank 3 equations are enough to generate the homogeneous ideal of X. So we prove that the span of the image of Q in this space contains all the old generators of the Veronese embedding. And this step is the hardest part of the proof. It requires around 10 steps or 10 case-by-case analysis. So anyway, by following these steps, we could prove the theorem A. And now I turn to the same kind of property for arbitrary projective varieties. By using the previous result about the Veronese embedding, we can obtain the following practical result for arbitrary varieties. So still, the characteristic is not equal to 2 and 3, and X is now a projective irreducible variety. And let A be a variant line bundle on X. So we can consider the embedding of X by A. And here, the integer m is defined as follows. So m is an integer such that this embedding is J normal, satisfies the J normality for all J bigger than or equal to m. And the homogeneous ideal of this embedding is generated by forms of degree and most m. So for example, you can take m to be the regularity of X when X is embedded by A. So such an integer must exist. In such a case, the else power of A satisfies prop QR of 3 for any L bigger than or equal to M. We could prove that asymptotically the power of A satisfies prop QR of 3. And here, let me provide some applications of this theorem. So here X is the Grassmannian manifold, and the A is the generator, the variant line bundle which generates the Picard group. So it defines the so-called Flock embedding. Then the Flock embedding is projectively normal, so it satisfies normality for all positive integer, and also its ideal is generated by quadratic polynomials, which are called the Flock relations. So you can take M to be 2. So okay, so for such X and A, X comma A to the L satisfies prop QR of 3 for all L bigger than or equal to 2. So except the Flock embedding, all embeddings of the Grassmannian satisfies this property. And on the other hand, for the Flock embedding itself, property QR5 fails to hold indeed. That is because the Grassmannian of lines in T3 is a quadratic, smooth quadratic hypersurface in T5. So it has its ideal is defined, generated by length 6 quadratic polynomial, and arbitrary Flock embedding has such a quadratic hypersurface as a linear section. So for any Grassmannian, for any Flock embedding, you can show that property QR5 fails to hold. And another example is we can apply the theorem to the Ein-Lagerfeld theorem. So X is a smooth complex variety of dimension n, and A is very ample line bundle. Then this line bundle, so this line bundle times the F line bundle is generated by quadratic polynomials by Ein and Lagerfeld. So in this case, again, you can take A M to be 2. So the square of this line bundle satisfies the property QR of 3. And our guiding problem was that the property QR3 holds for sufficiently ample line bundles as a property QR4. We want to answer for this question if the property QR of 3 holds for all sufficiently ample line bundles. And our study gives a partial answer for this question. So when characteristic is not equal to 2 and 3, and X is the projective space, then we proved that X comma L satisfies this property if L times O1 inverse is ample. And this means that L is OB, where B is bigger than or equal to 2. So property QR3 holds for L. And so what I want to say is, so in this simple case, the above conjecture is true. And for Grassmannian, again, here A is the very ample generator of the Picard group, and if L times A inverse is ample, then L satisfies property QR3. So again, well, so if the Picard group is simply generated, then indeed the conjecture is true. And when X is a smooth complex variety, in the previous slide, I mentioned that this type of line bundle is satisfies the property QR of 3 if this line bundle is a square of an ample line bundle. So if this line bundle times B square, where B is ample, then property QR3 holds. And if we tensor B cubed, then we don't know yet if this satisfies QR3 or not. And if B to the 4th power, then again, this line model satisfies QR3. What I want to say is this part is a fixed line bundle on X, and if we multiply a square of an ample line bundle, then property QR4 holds. And still, because we rely on the Veronese embeddings, so you can't deal with this type of line bundles. But still, the third example supports that the conjecture will be true. And we have a case where the conjecture is true. That is, if C is a projective integral curve of arithmetic genus G, and L is a line bundle of degree D on C, then if the degree is sufficiently large, then CL satisfies the property Q of 3. So for curve case, again, the conjecture is true. And here we have some explicit bound. So if the genus is 0 or 1, then the degree D should be bigger than or equal to 2 times genus plus 2. And if genus is bigger than or equal to 2, then the degree requires this condition. Degree is bigger than or equal to 4 times the genus plus 4. So as I mentioned, many classical varieties are determinantly presented, and hence their ideals are generated by rank and most 4 quadratic polynomials. So we asked to ourselves whether we can improve this bound of the rank. And as I mentioned through this talk, in many cases, we can show that asymptotically the property QR3 also holds. So we believe that property QR3 is also a property such that for any sufficiently ample line bundles, the property QR3 holds. Okay, so I stop here. Thank you.
Okay, thank you very much for the nice talk. Are there any questions or comments to the speaker? Oh, then I would have a question. So you mentioned that the last so that's the XL satisfy QR3 if it's such a line bundle is a square of an ample line bundle. And I think as being a square of an ample line bundle sounds too strong. So are there any counterexamples like that? L is of the form of K tensor A to the n to the plus 2 to the square tensor B and B square satisfy QR3, but QR3 fails of the form tensor by B to the 3, B cubed.
No, we believe that here, if we multiply any ample line bundle to this line bundle, then property QR3 will be true. But technically, our approach depends on the Veronese embedding, so we couldn't prove such a case. And we don't know any counterexample. Yeah.
Mm-hmm. I see. And I have another question. So I'm not sure that this is a good questions, but for instance, so it seems to be that most varieties, if it is sufficiently positively embedded, then it would get to satisfy QR3. So it was a rank of a quadratic generators. And probably, so assume that X is positively embedded, sufficiently positive embedded, and consider its second variety, then the ideal will be generated by cubics. And can we say something about, for instance, Waring rank of cubic generators of secant variety?
Yeah, that would be an interesting question. So as our philosophy is that the rank of quadrics will be a measure of the simplicity of the structure of the idea. So maybe that kind of principle will be true, but we have no idea how to approach.
I see. So are there any more questions or comments? No? Then please give a big hand to the speaker again.
Thank you.
So we will continue after 25 minutes of break.